Okay, so what do loudspeakers, megaphones, headphones, and these earbuds have in common? Well, they all use a motor effect to make something vibrate, which will make sound. So let's look at the inside. So here we've got the cross section of a magnet, and attached to that we've got a cone, or sometimes called a diaphragm. And then attached to that we've got a coil of wire. So the coil of wire attaches the cone to near the magnet. Okay, and the coil of wire has an AC current going through it, so that's very important. So the current's always changing direction within the coil. If we look at the particles in front, the cone is going to push the particles back and forth like this. So that's how it creates that longitudinal wave, which is what sound is. So we're going to look at how and why the cone pushes the air particles like this. How does the wire and the current in the wire interact with the magnetic field? Okay, so when we put a current through it, let's say the current is going around like this at this instant in time. So if we zoom into the top part, the current is coming from below us and then going around and away from us to the top. So the current is going into the page. And if we apply Fleming's left-hand rule at the top section, the force is towards the right. And then if we zoom into the bottom section, the current is coming towards us, okay, in the coil. So it's coming out of the page. And if we apply Fleming's left-hand rule again, the force is towards right. So that means the coil is going to be pushed towards right, and the coil is attached to the cone, so they're both going to be pushed towards the right. Then the current is going to change direction. Okay, so because it's an alternating current, right? So it's changing direction. Now, if we zoom in again to the top section, this time the current's out of the page, is coming away from the back end coming towards us. So apply Fleming's left-hand rule, the force actually towards the left. And if we zoom at the bottom section, the current is actually going into the page, so it's going away from us. So again, Fleming's left-hand rule, and the force is towards that. So now you can see the force has actually changed direction inside the coil, and the force on the coil has changed direction, so has the force on the cone. So the cone moves backwards towards the left, and this process is just going to keep repeating. So keep repeating left and right, and because it's an alternating current, and so the air particles in front of it get pushed left and right. Okay, so they oscillate parallel to the direction of energy transfer. In other words, we've just created a longitudinal wave. Okay, in this example, students attempt to explain how a loudspeaker produces sound. Suggest some improvements to the student's answer. So the first section says the current through the coil produces a force on the coil. So first of all, it's an alternating current that goes through the coil. And we can also say the current produces a magnetic field around the coil, and that interacts with the magnetic field that's already there to produce a force on the coil. The next part says this causes the cone to move towards the left and right. Now we've just skipped a bunch of steps there, so let's move that down and add some extra detail. So first of all, the coil and the cone both are pushed initially towards the left or right in one direction, and then when the current changes direction, the force also changes direction, and they're pulled back in the opposite direction. So this causes the cone and the coil to oscillate. Okay, they're pushing back and forth on the air particles in front as well, and that's what produces the sound waves. Suggest a change that can be done to increase the wavelength of the sound produced. So if you remember, wave speed is wavelength times frequency. And if we rearrange this for wavelength, if we want to make the wavelength longer, increase the left-hand side there, we need to decrease the frequency. Okay? So to decrease the frequency, we need to decrease the frequency of the sound. We have to actually decrease the frequency of the alternating current that we're using. So in other words, if the alternating current is changing direction less often, then the force on the cone will change direction less often. So the particles will change direction less often. So in other words, the frequency of the sound produced is smaller and the wavelength will be longer. It suggests 3 ways to make the sound louder. To make the sound louder, we need to make that force that's exerted on the cone bigger so that it pushes the air particles with a bigger force. In order to do that, to create a bigger force, a motor effect, increase the motor effect, use a larger current. If you use a larger current, there's going to be a stronger magnetic field around the coil, and that interacts more with the magnetic field that's already there and produce a big force. Another thing we can use is we can just replace the permanent magnet there with a stronger permanent magnet, and that would also increase the force. Finally, we can increase the number of turns of the coil. If there's more turns of the coil, each one experience a force, there's going to be overall, the resultant force will be larger, and that means it will push the air particles to the bigger speed. Remember not to say increase the coils, okay? So increase the number of turns of the coil.